Hi, so for today we're going to talk about the applications of first order differential equation in electrical circuits, more specifically in RL circuits, the resistor inductor circuits. That's what RL stands for, resistor inductor. Okay, so we have this differential equation here wherein we have L, which stands for the inductance in a circuit, okay, multiplied by the change in current with respect to time plus I, which is the current in amperes, multiplied by the R, which is the resistance in ohms, is equal to E, of which E is the voltage source in volts of our circuit. Okay, consider this schematic symbols right here, or basic circuit here, wherein we have the voltage source E and the resistor R and the inductor L, and we have a switch here connected in series. Now, if I close the switch here, definitely current will flow, charging this inductor, or in other words, coil, okay, wherein this inductor basically stores energy in the form of magnetic field by current flowing through it. Okay? So it is important that when we are analyzing RL circuits, or the application of DE in electrical circuits in RL circuits, that the configuration of the circuit must be in series. Okay? And this voltage source is in DC. Okay? So this is the formula. This is the key formula. Okay? This is our differential equation. And you need to memorize actually this. Okay? So at least familiarize ourselves when we are dealing with RL circuits. So again, let's try to, by the way, the unit of inductance is henries, okay, denoted by big letter H. The unit of resistance is in terms of ohms in this symbol. The current in amperes, big letter A, denoted by big letter A, and the voltage source in volts, big letter D. So let's try to solve some problems. So for number one, an inductance of L henries and the resistance of 10 ohms are connected in series. Okay, this is very important that they should be connected in series with an EMF of 100 volts. EMF stands for the voltage source, okay, or in other words, voltage source, okay, voltage in the circuit. So 100 volts. If the current is initially 0 and is equal to 9 amperes after 1 second, find L and find the current after 0.5 seconds. So we have our solution, wherein if we are going to recall our differential equation a while ago, this is our equation. And the first thing we are going to do is we have the given, okay? We have L henries, okay? Di over dt plus, okay, we have 10 ohms, okay? So that is 10 multiplied by the current I, okay? So that is our given because we cannot actually know first the current because the current is changing with respect to time. Okay? So that is why we have I in here. Okay? So equal to E, which is 100 volts. Okay? So what will happen here is that if we have this kind of equation, what are we going to do? Okay? So we simply plug in this equation. So as you can see here, if I'm going to divide this whole side of the equation by L, what will happen? I have di over dt plus 10I over L is equals to 100 over L. The problem is actually asking us what is the value of the inductance L. So we're going to solve for L. So as you can see here, this is a linear equation. If I'm going to rearrange this such that I'm going to isolate I, okay, in this, that is now linear. This equation now is linear in I. Okay? So if you are going to recall, okay, from our previous study, we have the linear in Y in the form of, we have this, okay? Wherein in order for us, this is linear in Y. So it's not always variable Y and variable X. In the application, we will be having I and T here. Okay? So in this linear equation, linear in Y, we can solve this linear, if you're going to recall our video, okay, we can solve this linear equation in the form of this as Y integral of E, y multiplied by e, integral of p of x dx is now equal to the integral of q of x e raised to p of x dx and dx here. Okay? This is the formula if we have a linear in y. How about if that is linear in I? That is still the same, but your variable will only change. So, this is linear in I, so we have I here because this equation is linear in y, therefore we have y here. Okay? And we have e raised to, what is our p of x? Our p of x, by the way, will be this, 10 over L. And we have what? Okay? Integrating with respect to the independent variable. So as you can see here, the dx is the independent variable, the x. Okay, so we integrate with respect to x. And in this equation, the independent variable is t, so we integrate with respect to t. Okay, and now equal to integral of q of x, which is 100 over L e raised to, copy this is the same, 10 over L dt, and we have dt also. Okay, so we can solve now for our L. So we have I e integral of 10 over L dt. So we are integrating with respect to t. So we can factor out 10 over L because we are integrating with respect to t, and this term has no any term containing t. So I can factor that outside of the integral. So we have dt here, okay, equals, okay, 100 over L. I'm integrating with respect to dt, so I can factor out that outside of the integral, and we are left the same with this 10 over L integral of dt, and we have dt here. So if we're going to integrate that we have I e raised to 10 over L, integral of dt is simply t, is equal to 100 over L, integral of this, okay, e raised to 10 over L, t, and we have dt in here. Okay? So I hope you can follow. Okay? So this left side remains 10 over L, t, i.e. raised to 10 over L, t, and we have 100 over L. Okay? How do we integrate this? Okay? Remember that we are integrating with respect to dt. Okay? So, any other term here, okay, 10 over L is considered as a constant because it does not have t. So, we have t in here. So, if we let u as equal to 10 over L, t, okay, differentiate it with respect to t. So, we have 10 over L dt. Correct? Because the integral or the derivative of this is considered as constant, and the derivative of t is simply 1. So we have 10 over L dt. And if we're going to express, okay, dt, because that is what we have here, dt, so we have L over 10 du. So we can simply substitute that to our integral. So we have now e, okay, raised to u, of which u is equal to 10 over L t, and we have dt is now equal to L over 10 multiplied by du. Now, I can factor out again L over 10 because we are integrating with respect to du. That's right. 100 over L multiplied by L over 10, the integral of eu du. So, we can see here that this would cancel out, and we have what? We have 100 over 10, that is simply equal to 100 over 10, 10. Okay, and the integral of eu du is e raised to u plus c. But, okay, we must back substitute the value of u. So, we have u 10 over L t. Okay, so that our equation will now become 10 over L times t is equal to 10 e raised to 10 t over L plus c. Now, we can express the left side of the equation in terms of current by dividing both sides by e raised to 10 over Lt. So what will happen? We have I, if we divide this both sides by e raised to 10 over L, so we have 10 e raised to 10 over Lt over e raised to 10 over Lt plus c over e raised to 10 over Lt. Okay, and we know that this should cancel. So we are left with I as 10 plus, okay, we have C over E raised to 10 over L multiplied by T. So, this is our solution for our differential equation containing the arbitrary constant C. Okay? So, now, in order for us to find L, okay, we need some certain condition. Okay? But we know that our problem has given initial condition for I. Okay? And we have another condition that if time is equals to 1 second, the current is 9 amperes. So what will happen here is that we need to find still the value of C by plugging in the what? The initial condition. It says here, okay, if the current is initially 0, okay, so we must take that condition. If the current is initially 0, that means that time is equal to 0, current is equal to 0. Plugging it into our equation, we can find the value of C. And we have I is equal to 0, 10 plus C over E raised to 10 over L multiplied by 0 because time is 0. So this is simply E raised to 0. So this would become simply equal to 1. And C over 1 is 1. So we have 0 is equal to 10 plus C. Now, the value of our C would now become negative 10. Okay? And if we plug in negative 10 in our model equation here, so we have now the particular solution of the D as I is equal to 10 minus, because that is a negative, so minus 10 over, okay, E raised to 10 over L multiplied by T. And we can now find the value of L by plugging in or by simply substituting the second condition. Okay? The second condition tells us the current is equal to 9 amperes after 1 second. So, if the current is equal to 9 amperes at time is equals to 1 second, I can therefore find the value of L by plugging in these values in our equation. So, we have 9 is equals to 10 minus 10 over E raised to 10 over L, okay, multiplied by 1, which is simply E raised to 10 over L. So what will happen here if I'm going to find the value of this L, okay, so we're going to have what? Going to have 9, okay, is now equal to 10 E raised to 10 over L minus 10, okay, over E raised to 10 over L. Okay? So, if I'm going to cross multiply this, we have this, let's say, let me just delete this first. Okay? So, we have 9E raised to 10 over L, okay, is equals to 10E raised to 10 over L minus 10. Cross multiplying, okay? We cross multiply, combining like terms, you have 9 E raised to 10 over L minus 10 E raised to 10 over L is equals to negative 10. Okay, so we can subtract these two. So because it has the same base, okay, variable here and the same exponent here, so we can simply subtract this. So that would be negative E raised to 10 over L is equals to negative 10. If I'm going to what? Okay, to multiply them both sides by negative 1. So what will happen? We have E raised to 10 over L is equals to 10. And taking the ln of both sides, okay, why do I need to do this? Because L is in terms of exponent. E raised to 10 over L, ln of 10. So ln of E simply would cancel, and whatever the exponent is, that would be the remaining term. Okay, so we have ln of 10. So solving for L, so if we solve for L, that is L is equal now to 10 over ln of 10. And if we are going to solve for that using our calculator, we will find that the answer should be, the inductance is 4.34. The unit of inductance is Henry, or in terms of H. Okay. So this would be our inductance. Okay, L. And the other question, it says on the other question is find the current after 0.5 seconds. So after 0.5 seconds, you can see we have now the model equation, which is this. Okay, we can find the current, okay, at any time t, as long as we know the value of L. Okay, the value of L here does not change. The only thing that is changing here is the value of current, okay, with respect to time, because our formula is di over the LDI over dt plus IR is equals to E. So there is a change in current with respect to time. So if I'm going to plug in I, our model equation is I is equals to 10 minus 10 over e raised to 10 over 4.34. Okay? E raised to 4.34. Let me just rewrite this. So this should be e raised to 10 over 4.34, which is the value of L, multiplied by t. So if we're going to solve for the current at time is equals to 0.5 second, we can simply plug in the value of 0.5 second and solve for our current, since we have already the model equation for our problem. So we have 4.34 multiplied by 0.5. And let me just solve this. So we have 10 minus 10 over e raised to 10 over 4.34 times 0.5. And the current is 6.84 amperes. So 6.84 amperes. Okay, so that's the current. Okay. Okay, let's proceed to another example. So an inductance of 1 Henry and a resistance of 2 ohms are connected again in series with a constant EMF of E volts. If the current is initially 0 and is equal to 10 amperes after 5 seconds, find the value of E, or the voltage source. So let me just first rewrite again our formula. di dt, LDI dt plus I times R is equals to E. And we're going to plug in the given. We have 1 Henry, that is in terms of L, di over dt, that is the value of our L, 1 Henry, plus we have 2, okay, because we have R is equals to 2, and I is changing with respect to time, so we must write simply I, and now equal to E. So simply we have a differential equation of di dt plus 2I is equals to E. Okay? So if we are going to solve this, we have di dt is equals to E minus 2I. Okay? This is a variable separable problem wherein I can, this one, E minus 2I, I can group this with di, E minus 2I. Let me just rewrite this and have a little space. Okay? So we have di is equals to over E minus 2I is equals to, cross multiplying, we have dt here. And if I'm going to integrate both sides of the equation, okay, so we are given a certain condition. We have two conditions here. And if we're going to write the condition, okay, the first condition is says if the current is initially 0, that is equivalent to at time is equals to 0 and I is equals to 0. And the second condition is that we have I is equal to and is equal to 10 amperes after 5 seconds. So the current is 10 amperes after 5 seconds. So we have a time is equals to 5 seconds. We have I is equals to 10 amperes. Okay. We are integrating these two sides by variable separable. Okay. So what will happen here is that this is in terms of current, this is in terms of time. So if we want to find the value of E, we can simply substitute this as our limits for the integration. So we have at time, okay, at time is equals to 0, okay, the current is 0. This is in time, this is in current. So we have the lower limits of time and current, which is actually 0. So we have at time is equals to 5 seconds, the current is 10 amperes, okay? So we write the limits and we need to integrate this and evaluate the limit so that we can find E. So first, how do we integrate this? Okay, we are integrating with respect to di. Okay, so any term that is not in terms of I is considered as constant, as well as the E here. So if I'm going to make let U as equals to E minus 2I, okay, so du with respect to I is negative 2 d DI. Okay, so if I'm going to get DI, okay, because we have DI here, so I will be having negative 1/2 du is equals to DI. Okay, so if I'm going to substitute this, so what will happen here is that we have what? Okay, negative 1/2 du over u evaluated from 0 to 10. Okay, our u is this, our du is this, okay, or di is this, is equivalent to the integral of from 0 to 5 of dt. Okay, this is simple integral. Okay, so I can factor out what? Negative 1/2 the integral of du over u evaluated from 0 to 10 is equal to integral of dt evaluated from 0 to 5. So what will happen is that we know that that is negative 1/2. Okay, this is outside of the integral. So we have ln of u, of which our u is e minus 2i. E minus 2i, okay, evaluated from 0 to 10. Okay, take note that this negative 1/2 is outside of the integral, so we need to multiply them both by when this function is evaluated from 0 and when this function is evaluated from. So, and we have integral of t evaluated from 0 to 5. So, simply we substitute the limits. So, we have negative 1/2. We have ln e minus 2 times 10. Okay. So, this is with respect to I. So, we substitute the value of the upper limit minus the lower limit. E minus 2 times 0. Okay, is equal to 5 minus 0. So, evaluating the limits from that. So, we have negative 1/2 of ln e minus 20. And this is minus ln of e. Because 2 times 0 is 0. Is equals to 5. Okay? That is our equation. And we can find e. Okay? So, if I'm going to multiply both sides of the equation, let's say, to eliminate this 1/2 by negative 2. So what will happen is that we're going to have ln e minus 20 minus ln of e is now equal to negative 10. Okay? And by properties of ln, I can rewrite this if we have a minus, okay, as the numerator minus over the denominator of this. So ln e minus 20 over e. That's the property of logarithm. Natural logarithm. Wherein if we have a difference of ln, we can write this inside of the ln as our numerator and this is the denominator. If we have a plus, we can multiply them inside. Okay? So since we have a minus, we have a fraction right here. So negative 10. So if I'm going to exponentialize both sides, okay, such that I'm going to put e, okay, on the left side and on the right side of the equation, whatever you do on the left side, you're going to do it also on the right side. So this should cancel. We know that that is e minus 20 over e, and this is e raised to negative 10. And if I'm going to cross multiply this, this is e minus 20 is equals to e multiplied by e raised to negative 10. Okay, combining like terms, we have e transposing this. Oops, we transpose this. We have minus e raised to negative 10. E times e raised to negative 10 is equal to, if I'm going to transpose this, this would be 20. Okay, if we factor out e, we can factor that out. Minus e raised to negative 10 is equal to 20. Therefore, isolating e, we have e is now equal to 20 over 1 minus e raised to negative 10. And if we're going to solve that using our calculator, okay, so we have an answer of 20 volts. Okay, and that is the value that the problem is trying to look for. What is the value of the voltage source? Okay, so the answer here in our problem number 2 is actually 20 volts. Okay, let's go on to our last problem. Okay, so in a series RL circuit, L is equal to 4 Henrys, R is equal to 100 ohms, and E is equal to 200 volts. find the values of current as a function of time. So we are asked to find an equation, what is the current at any time t as a function of time. Assume that the initial current is 0. Find the current when time is equal to 2 seconds. So let me just rewrite again the formula. LDI dt plus IR is equals to E. We are given 4 Henrys, so we have 4 di dt plus our resistance is 100 multiplied by I is equal to E, which is 200. If I'm going to divide both sides of our equation by 4, we have di over dt plus 25I is equals to 50. Okay? And as you can see here, again, we have a linear equation. Okay? So we can also solve this using variable separable, that just like what I did a while ago. And we can also solve this in linear, but I'm going to show you the linear. So this is already linear in I. Okay? Linear in I. If that is a linear in I can solve that by having the formula I e raised to, okay, we have p of x, which is 25, okay, dt is equal now to q of x, which is integral of 50 e in raised to the integral of the same, this one. So we have 25 dt and integrated with an integrand of dv. Okay, so with respect to d, so we have I e 25t, because we can factor out 25, the integral of this 25t is equal to, I can factor out 50 integral e raised to 25t dt. Okay, so all that we are going to do is first, what? Integrate this again. So we have e raised to 25 I times e raised to 25t times 50. So if we integrate this, let u as 25t, du with respect to p is 25 dt. So I don't have any 25 dt here. So if I'm going to express this as u, so we have e raised to u. Our dt is simply, from this equation, we have du over 25. So I have du over 25. So I can factor out 1 over 25 because that's a constant. So we have 50 over 25. Okay? Or 25, I mean. So we have 25 in here. Integral of e raised to u du. So we can finally get the general solution for this dE. 50 over 25 is 2 e raised to u plus c, wherein if we back substitute the value of u, it turns out that that is equal to what? 25t, okay, plus c. So, of course, if we plug in directly the condition here, we cannot solve for the current, okay, because we don't know the value of c. Okay, so we first need to find the value of c by having the first condition. It says, assume that the initial current is 0. So, at time is equal to 0, current is equal to 0. So, what will happen if I'm going to plug this in our equation? So, we have I is equal to 0. Then definitely the left side of the equation will become 0. Because 0 and times any number would be 0. Okay? Multiplied by is equal to 2 e raised to 25 times 0 plus c. So e raised to 25 times 0, 25 times 0 is 0. E raised to 0 is 1. So 0 is equal to 2 plus c. Therefore, c is equal to negative 2. Okay? So what will happen is that we have now an equation that is, okay, I e raised to 25t is equals to 2 e raised to 25t minus 2. Okay, because our value of c is negative 2. And if I'm going to express this as a function of time, this left side of the equation as a function of time, we have e, I'm going to divide both sides of the equation by e raised to 25t. So we have 2 e raised to 25t over e raised to 25t minus 2 over e raised to 25t. So you can see here that this should cancel out. This would cancel out. So we have now the formula I as a function of time as 2 minus 2, okay, minus 2 over e raised to 25t, or by loss of exponent, I can bring this up by negating the exponent. We have minus 2 e raised to negative 25 times t. Okay, this is our model equation, or the equation of time, or the equation of current as a function of time. Okay, that is our answer. And finally, now we can get the current. Find the current when time is equals to 2 seconds. So when at time is equals to 2 seconds, what is the current? Okay? So simply plug this in our equation. We have 2 minus 2 e raised to negative 25 multiplied by 2. And if we're going to calculate that, okay, so we will be getting an answer of simply 2. Okay? And the unit of current is 2 amperes. Okay? So that is our answer for this problem. So as you can see, solving RL circuit requires a knowledge of variable, separable, and solving linear equation. And first, we need to find the model equation if we are asked to find for the current at any time t. So what is the most important here is to memorize, at least familiarize yourself, or to memorize the equation here, okay, the differential equation here, and know how to solve using the given parameters, or given okay. So I hope you learned something from this video. Thank you so much for watching, and I hope you give this a thumbs up, and subscribe to my channel if you find this video helpful. Once again, thank you so much. This is Engineer Abat. Thank you and God bless.